There's a substance on nearly every pine tree within a mile of where you're sitting right now. It seeps from wounded bark and amber-colored beads. It smells like a forest. And when you mix it with crushed charcoal in the right ratio, you create a structural adhesive so effective that Neanderthals were using it 200,000 years ago. It survived buried in archaeological sites long enough for modern researchers to test it in a laboratory. And it has even been shown to outperform modern epoxy under impact stress. Archaeologists found this kind of glue in the ancient world too, the same adhesive once used to haft Ötzi the Iceman's axe. It costs nothing. You collect it by walking to a pine tree with a jar. And the adhesive industry generates $15 billion a year making sure you think you need a plastic tube from a hardware store instead. Here's the exact recipe. Every step. Everything you need to know to make it today. 2 ingredients. That is the entire formula. Pine resin. The amber or white crystallized sap that bleeds from any wound or crack in a pine, spruce, or fir tree. You collect it by pressing a jar against natural drips or old wound sites on bark. No damage to the tree needed. You're harvesting what it has already exuded. A single wound site on a mature pine can produce enough resin to fill a small jar in a season. It costs nothing but the walk. Charcoal. Crushed fine. Any charcoal from a campfire, a wood stove, or a fire pit. Grind it between 2 rocks or in a mortar until it is a fine black powder. No special equipment. This is exactly how it was done for 200,000 years. The ratio is critical, and it is documented in peer-reviewed archaeological testing. 10% charcoal by weight to 90% pine resin. That specific ratio, confirmed in a 2017 study published in the Journal of Archaeological Science, increased pine pitch shear strength from 0.37 megapascals to 1.77 megapascals. That is nearly 5 times stronger, not from a different material, from adding fine charcoal powder at exactly the right proportion to the same base resin. Here is how you process it. Place your collected pine resin in a metal tin or an old pot over a fire or camp stove. Heat it gently until it liquefies. Pine resin melts at around 80 degrees Celsius, well below boiling water. Do not boil it hard. Slow, gentle heat. As it liquefies, add your pre-measured charcoal powder and stir continuously. The mixture will turn from amber to deep black. Keep stirring for 5 to 10 minutes. This is called seething, and the 2017 study found that 10 minutes of seething at moderate heat maximizes adhesive strength. More than that begins to make it brittle. Less than that leaves performance on the table. Pour it into a mold or onto a non-stick surface to cool into a solid cake. This is your working stock. To use it, apply gentle heat to the bonding end of a stick, a knife handle, a wooden joint, a cracked tool handle, any application where you need a structural bond, and press the cake against the heated surface. The pitch softens on contact with heat and flows into the joint. Remove the heat. It cools in seconds to a hard, impact-resistant bond. Total cost, 0 if you have a pine tree and a fire pit. Under $5 if you buy a bag of lumped charcoal and have no pine trees nearby, in which case pine resin is also available, dried at herbalist suppliers and online for a few dollars a bag. Now here is why this works, and the science behind it is older than our species. Pine resin is composed primarily of rosin, a complex mixture of diterpene acids, and terpene solvents. When you heat pine resin, the volatile terpenes evaporate, and what remains is a concentrated thermoplastic adhesive matrix. It is hard at room temperature, pliable when warm, and bonds strongly to wood, bone, stone, and ceramic. Charcoal is not just filler. This is the part that most people get wrong when they try to make this and fail. Charcoal particles at the 10% ratio act as a mechanical reinforcement within the resin matrix, the same principle as rebar in concrete or carbon fiber in composite materials. The angular charcoal particles interlock within the resin as it cools, dramatically increasing its resistance to shear forces and impact. The 2017 Journal of Archaeological Science study, conducted using the same lap shear testing standards applied to modern industrial adhesives, found that 10% charcoal addition produced the peak strength increase. Below that, and you leave reinforcement potential unused. Above 20%, and the charcoal begins to act as a crack initiator rather than a reinforcer, and strength drops. This is not folk knowledge. This is documented materials, science applied to a recipe that Neanderthals empirically optimized 200,000 years before the laboratory confirmed why it worked. Now here is the history that adhesive manufacturers do not teach in schools. In 1991, a frozen body was discovered melting out of a glacier in the Ötztal Alps on the border of Austria and Italy. He had been preserved in ice for 5,300 years. His name, the name researchers gave him, is Ötzi the Iceman, and among his possessions was a copper axe. The blade was hafted to the handle using birch bark pitch reinforced with leather bindings. That joint had held for 5,300 years of freeze-thaw cycling, glacial compression, and complete submersion in ice. Show me a tube of modern epoxy with a 5,300-year track record. The oldest chemically identified adhesive in Europe dates to 200,000 years ago, produced by Neanderthals, not anatomically modern humans. The same beings we spent decades assuming were cognitively primitive. Researchers at the Max Planck Institute for Evolutionary Anthropology found that producing functional pitch adhesive required controlled multi-stage fire management, forward planning of material collection, and precise heat regulation. They published their conclusion directly. The cognitive demands of Neolithic adhesive production were equivalent to those required for compound tool manufacture, tasks previously used as markers of advanced intelligence. The adhesive in Ötzi's axe was not primitive. It was engineered. And the engineering principles, thermoplastic resin, mechanical reinforcement through particulate additive, joint preparation through heat, are identical to the principles in modern structural adhesive design. The difference is that ours costs $15 a tube, requires a chemical supply chain spanning multiple continents, cures in a narrow temperature window, and becomes brittle over time as the polymer chains degrade from UV exposure. The Neolithic version costs nothing, cures on contact with cooling air, tolerates impact forces better than static shear, and has a demonstrated field lifespan of over 5,000 years. Here's the number the adhesive industry does not want you doing the math on. The global adhesive market was valued at $15 billion in 2023. The DIY and home repair segment alone generates several billion of that annually, sold to people fixing furniture, repairing handles, sealing cracks, hafting tool heads, patching ceramic, products that fail within months under outdoor UV exposure, products that become brittle in cold, products sold in single-use tubes designed to run out before the job is done. Pine resin plus charcoal pitch is thermoplastic. It does not degrade from UV the way synthetic polymer adhesives do, because it was produced in an ultraviolet environment and is already photostabilized by its natural chemistry. It is reworkable. If a joint fails, you apply heat, reflow the adhesive, reset the joint, let it cool. No new material needed. The same batch of pitch can be repaired, resoftened, and reused indefinitely. A tube of epoxy is a one-time use. A cake of pine pitch is a lifetime tool. The adhesive industry's business model requires you to run out and buy another tube. A material that is free, self-sourcing, and indefinitely reusable from the nearest pine tree is not a business model. It is a business ending. 3 things to know before you make your first batch. Temperature sensitivity. Pine pitch softens at around 60 to 80 degrees Celsius. This makes it perfect for tool handles, wooden joints, ceramic repair, and any application where the bond will not be exposed to sustained high heat. It is not appropriate for applications directly adjacent to a heat source, stove repairs, engine parts, fireplace components. For those, you need a different material. For everything else, it outperforms epoxy on impact resistance and equals or exceeds it on shear strength when made correctly. Surface preparation. Clean, dry surfaces bond better. Lightly sand, or score the bonding surfaces if they are smooth. The mechanical key improves adhesion the same way it does with any adhesive. Heat both surfaces briefly before application, so the pitch flows fully into the joint rather than solidifying on contact with cold material. Now let's talk about the ratio discipline. The 10% charcoal figure is not approximate. Too little, and you lose the reinforcement benefit. Too much, and you introduce brittleness. Weigh your ingredients if you can. A kitchen scale accurate to 1 gram is a $2 investment that makes the difference between a joint that holds and one that fails. Mix by weight, not by eye. One more application most people miss entirely. Pine pitch waterproofs. Ancient Scandinavian shipbuilders sealed hull planks with pine tar, a related product from the same tree. Native American tribes waterproofed baskets, canoes, and water vessels with pine resin for thousands of years before European contact. A thin coat of softened pine pitch painted onto a wooden surface, allowed to cool and harden, creates a moisture barrier that has outlasted every synthetic waterproofing product ever sold. Your wooden tool handles, your raised bed joints, the cracks in your cold frames, the seams on a wooden planter that keeps splitting. One application of pine pitch, $0, lasts years. The pine tree growing in your yard is a hardware store. The adhesive industry just never told you the address. That's it for me today. Hope you learned a lot, and I'll see you in the next one.